Thank you everyone for joining today. My name is Matt Cope. I'm a Principal Solution Architect here at AWS. And I'm excited today to talk about numerical weather predictions and specifically how we optimize these on our AWS Graviton2 instances. So some of you may not be real familiar with numerical weather predictions, or you may not really know much about Graviton2. Today, I'm going to be able to talk about both of these items as well as provide some background in case you haven't been exposed to it before. So today, our agenda will be first, some background. What is numerical weather prediction and why does it matter? And really, how does it map to high performance computing? Second, I'm going to talk about Graviton2. Really, what is it? How does it relate to this? And what value could you get out of it? Second part is more of the details on running on Graviton2. So how can we set up a high performance computing environment to be able to use Graviton2-based instances? Second, what's different about running on Graviton2? We'll share some tips and tricks, as well as some other questions that other customers have asked in the past about using Graviton2. Next, we're going to talk specifically about one numerical weather prediction model. We're going to specifically talk about the Weather and Research Forecast model, or the WRF model. We're going to talk about common optimization areas that we should look at in WRF, as well as other numerical weather prediction models. Next, we're going to talk about performance. Right, so not only can we see if we can run, what's really the performance we get out of using these new instances. And then finally, we'll wrap up with a summary on exactly what we learned, as well as some pointers to other materials to be able to go try this stuff out on your own. So numerical weather prediction, or NWP. At a very high level, this is how do we take current weather observations? So this is like, what's the weather outside today? What's the temperature? What's the humidity? What's the cloud cover? All of these variables. And based on that, try to generate the forecast based on that model. So you can see it right. We have a forecast essentially of surface wind speed over a given period, which is given to us by one of our customers who uses WRF, DTN. We can use weather forecasts for numerous different applications. So most of us probably think about it in terms of it tells us whether we need to pick up an umbrella or if it's a good idea to cancel our trip, to maybe the local park, in 2 days from now, right? It helps us kind of guide those. But it's used by a lot of other organizations to make other decisions. So it could be, what's the weather going to be like in terms of, wildfire prediction? Right, that matters. What's the moisture? What's the winds? What are all of these other variables? It could be, what's the amount of sunlight my solar array is going to have, right? Or it could be very localized prediction to understand the impact of upcoming weather on crops and yields and how you should water. Could be a number of these different applications. So it's a very widely applicable problem and a very interesting one. Now, as I mentioned before, for this talk, we're talking specifically about the Weather Research and Forecasting, or WRF model. It's one of dozens of different models that are available, but it's a very popular one and used by a number of our customers. So again, we're going to focus on WRF. However, the lessons that we talk about here can really be applied to many other models, as well as HPC applications. So a lot of what we say, even if you're not running weather prediction, maybe you're running a computational fluid dynamics model that's looking at a pump design or a wing design, a lot of the same commentary and guides can be used there as well. So I want to provide a very simplified version of how do we forecast the weather. For those of you that are experts in numerical weather forecasting, this is going to seem like a gross simplification. However, I do want to provide sort of the basic understanding of how does this work and some of the key elements we need to keep in mind for performance, because that will tell us, is Graviton2 a good place to start for this sort of workload? So the first thing, as I said before, is with numerical weather prediction, we have to start with the initial data. Right? We have to know what does that particular area look like today, as well as the area around it. So if you think about it, if it's currently raining outside, 1 minute from now, it's probably going to be raining, right? Especially if I can see the cloud nearby. However, it starts getting trickier the further and further out we go. So we have to feed it excellent initial data, which is generally provided by weather stations around the world, as well as other information that's useful to help predict future conditions, such as topological information, right? If something is in a canyon or there's a giant mountain in front of something, right, that will heavily impact what happens to in the future. Also, other assumptions, right? So many of these things we can't directly calculate because it would be incredibly computationally complex, but we can add in certain assumptions around, we think this part of our model is, say, covered by forests, right? That will interact very differently than, say, a cityscape, which is mostly concrete. So we have to take in all of this initial data, which can include data about not only what the weather is, topological information, and others, and we use that to initialize our model. So the way we look at this is, how do we do things in time steps? We know what it is right now, and then we say, what's it going to look like in 5 minutes? We use a variety of physical models that we have validated to be able to best simulate what will happen in 5 minutes. Similarly, we use that data from for the next forecast to deliver another 5 minutes or whatever granularity we were interested in to continue simulating. So these are really what we call time steps. And we continue this until we've kind of reached the end of what our forecast period would be. So as you would expect, as the forecasts get longer and longer, we're relying on the data we previously computed. So if our initial data isn't quite correct, right, it will get worse towards the further we go out. And really that's why forecasts are harder in so much further in the future, because there's frankly not enough initial data or enough computational power to be able to solve that problem. Now, the other part to keep in mind here is it's not just putting in data and then outputting data at the very end with what the forecast will be in maybe 8 hours or 2 days or whatever the period might be. We want to know what happens in between, right? We don't necessarily want to know exactly in 8 days. We want to know every half hour, perhaps, in between now and the forecast period. And so we're doing IO operations to write out that data at scheduled forecasted times. So that's kind of a high level overview of how this works. Now, let's make it a little bit more concrete. So let's say we're trying to forecast this particular region. This is the southeast section of the United States. And we want to forecast maybe the weather for the next day. And we want it to be pretty high resolution. We don't want it to be just super basic. We want it to be pretty high resolution. So if we wanted to solve this very quickly, a single server probably is not going to work, right? Because it's a lot of computation, it's a lot of data, it's a lot of physical models that we need to think about. And especially for a lot of those use cases I was talking about, it's not real useful to have a forecast of something that comes out after the event's occurred. So if it takes me 12 hours to forecast 1 hour, that's probably not very useful, right? So we want to have a speed up that's considerably better than sort of what the real time we're forecasting is. So how can we do that? Well, the main way we do this is very similar to other sorts of applications for high performance computing. So we need to decompose the problem into smaller tasks called domain decomposition. In this case, a very simplified view is to say, let's split these up by the latitude and longitude of these particular locations, fit it by a grid. And then let's solve each of these individual components, because in some ways they're somewhat separate from each other. So if we think about how would we want one particular instance or server in this case to forecast this little section, which I marked as orange on the map? Well, what we need to know is all of the information about that area, right? I need to know what the current conditions are. Again, all of those other attributes that we might need. Now, to go back to the previous slide where we were thinking about How do we iterate through this? Well, I need to know what the current weather is. Let's say I forecast 5 minutes ahead. Now, I could keep going ahead based on what I already have, but I actually need to know information slightly outside of that as well, right? Because if there's a storm that is right on the left side, say in Mississippi on my image here, you kind of need to know that because that's likely to move into my slot here. And so at each of these different time steps, we need to do a communication across all of these sort of borders. And so the key part here is to understand that not only do we want to have all of this data local, but we also have to share it at each one of those time steps. And so the critical part about this is we want to do it very quickly, right? Because I can't forecast the next time step unless I have all of the information from all of my partners. Now, there's two elements of this. One is you want all of your partners to finish their computation at basically the same time, right? If it were to take the one of these segments 2 times as long to calculate it, you couldn't move on to the next one until that one was finished. So in essence, it would slow you down, that center area. And in fact, it slows everyone down because this is connected. So a single slow one of these ends up slowing the entire computation and the entire forecast down. So what we really want to make sure is each of our elements can be solved in a fairly consistent time frame. Further, we want those communications where I'm sharing data to be done very quickly and again consistently. So the part I want to show here is this is a high performance computing application that's a fairly demanding one. And so we haven't picked a model that's very simple. So when we look at Graviton 2, we can use this as also a proxy for other HPC applications, not just those in the numerical weather forecasting area. Now, again, this is a simplified view. You might also split these up into vertical domains as well as further segmentation for other sorts of opportunities. But again, this is a simplified view to kind of understand the basics of what we're doing with numerical weather prediction. All right. So now that we've kind of understood what problem we're looking at, what is Graviton 2? Some of you may have heard of Graviton 2 and said it's something about ARM. It looks like I can save money, right? We have a lot of materials around that can show you how to save money using Graviton 2. But does it really apply to high performance computing or numerical weather prediction? And so first, let's talk a little bit about what Graviton 2 is. So it's useful to start to think about it as it compares to other things you may be used to. So most of you who run HPC applications today are probably using an Intel or AMD-based processor. Those are really the vendors that we talk about when we say that. They also have brands that you may be familiar with. So Xeon brands their enterprise processors Xeon, and similarly, AMD calls them EPYC. And we have these instances based on both of these platforms here at AWS, and works great for a variety of workloads. And you can see that both of them, though, even though they're different vendors, different brands, they share the same instruction set architecture. So the instruction set architecture is really the low-level commands that you're giving the CPU. So what that means is if we've compiled something, and most times in HPC we're compiling a Fortran code or a C++ code, and we're compiling it into those instructions the CPU can execute, it means that I could probably take a code that's built on an Intel platform and run it on an AMD one, and vice versa. Again, it depends specifically on how optimized you made it when you compiled it, but they're very similar. Even if you have to recompile, there's generally not a lot of change in your application. Now, the other side here, which is on the left, is the Graviton processor brand. This is an AWS processor, and you can see the instruction set architecture isn't x86, something called ARM, or you may see it in Linux as AArch64. This is, again, a different way of passing the instructions to the CPU. Just like AMD and Intel have other versions of their processors, we also had a Graviton before we had a Graviton2. So the main part when we're thinking about instruction sets is even though you may have a code that was compiled and was running great on Intel, and you may have also tried an AMD, it won't work if it's a compiled code on AWS uh, unless you actually recompile it, because the end binary, which is the instructions we send to the CPU, is really not compatible because they're talking a different language. So this is kind of telling you why you may have heard ARM or Graviton2 and kind of what these things mean. So all of these platforms can be excellent choices, and we offer all of them here at AWS as well. But again, today we're going to talk about Graviton2. So as I said in the previous slide, we had a Graviton processor, but not a lot of people had necessarily heard about it. But Graviton was our first ARM processor here at AWS and really a first-class citizen in EC2. So you could spin it up, you could have AMIs, you could launch it, use all of our normal tooling around it. And it was a great way for customers to do a variety of different types of applications. But the other part was it was a great way for us to gather information about what our customers really wanted in a processor, as well as ensure that all of our tooling from, ensuring our operating systems, as well as through our partners, as well as our own services are able to handle ARM, right? It has some different requirements. So we wanted to make sure we were ready for that. So by the time we launched Graviton 2, we had all of the basics covered. And this processor, rather than being, a good processor, but not good enough to sort of run all of our customer workloads, we were able to set the stage for Graviton 2. You can see here, it has 4 times the number of vCPUs. We'll talk later. It has 64 different vCPUs. And in total, it has 7 times more CPU performance. If you kind of work backwards on the math there, that means that each of the vCPUs is roughly 2 times more performant than the one in the original Graviton. All right, and I also have this nanometer bit here, 7 nanometer. What's cool here is 7 nanometer is a leading chip fabrication process. So that's really kind of the size of different features in the chip. And so what that means is it was a very new processor utilizing the latest technology that allowed us to eke out more performance and better power performance. You can see it's also a very large chip. It has 30 billion transistors versus the 5 in our original Graviton. So here's a little bit more of the deep dive into kind of what this is. You can read these particular bullets, but the things I want to focus on are: one, it's not a completely proprietary design. So the cores on this particular chip are ARM Neoverse N1 cores. We work very closely with ARM in the development of this core to make sure it matched requirements of our customers. The great thing about this is standard compiler suites, GCC as well as the ARM compiler and others, have optimizations for the N1 core. And so there are 64 of these N1 cores on a Graviton 2 chip. Great part here means all the tooling that's out there will work great and is optimized to be able to run on this platform. The other part you want to keep in mind is often at AWS, we talk about vCPUs. And in HPC, we like to talk about physical cores. And so generally what you've said is, well, it has 72 vCPUs, which means it has 36 physical cores, because generally we have 2 vCPUs per physical core, because it's using something called simultaneous multi-threading, or hyper-threading is the Intel name for it. So in this platform, Graviton 2, there are no SMT threads. So every vCPU is a physical core. So when we say this platform has 64 vCPUs, it really has 64 physical cores. The other thing that's really interesting that's different from other platforms is there's no NUMA concerns. So NUMA, again, is non-uniform memory access. So if you have 2 processors in a single server, which is very common these days, you have to be very careful about how you access memory from a different socket of that server. So In the Graviton2 platforms, they're only single socket. And further, we've optimized the memory subsystem so every core sees the same path to memory. There's no weirdnesses about worrying about, am I connected to this particular memory channel or another? It gives you consistent performance across the board. And remember, consistency is one of the things we wanted to keep in mind for a platform that would run numerical weather forecasting well. All right, so that's a little bit about the chip itself. Now, we offer Graviton2-based instances in much the same way we do for Intel and AMD instances. We have C, M, R, X instances, and to further explain those, C kind of means compute optimized. It means I have a bunch of vCPUs and I have 2 gigabytes of memory per vCPU. M is a general purpose 4 gigabytes of memory per vCPU, and R is generally larger memory requirements, so 8 gigabytes per vCPU. Now, normally that would mean you just multiply the number of vCPUs by 4 in a C instance to tell you how many gigabytes you have per physical core. But remember, Graviton 2, we have each vCPU is actually a physical core. So if you're running your application in such a way that you're using one MPI process or rank per core, you're now going to have 2 gigabytes per core rather than 4 gigabytes per core on an Intel-based one for, say, the C instances. Now, this may seem, well, I really need 4 gigabytes per physical core. I recommend that you try your application out, because in many ways, especially for applications that scale and parallelize very well, such as numerical weather forecasting apps, these are less powerful physical cores compared to, say, the Intel Skylake processor. However, we have more of them, right? So you can further do that decomposition across more cores. So you don't actually need to have quite as much memory per vCPU. But if you do, right, you can always move up to the next size up. So we have M, R, as well as X instances, which give you 16 gigabytes per vCPU. So really, we have a number of different options. We also have variants that allow you to have local disk, just like we do for our Intel and AMD instances. We also have some instances that provide higher network capability. So as we'll see in a few minutes, we have a C6GN 16 extra large, which adds 100 gigabit networking capabilities, as well as our elastic fabric adapter. An elastic fabric adapter, as we'll talk about a little bit later, is our high performance networking when we need to do tightly coupled sorts of applications like numerical weather forecasting. So we now know more about Graviton2 and kind of how it fits into AWS. Now, how do we run applications on Graviton2? You want to get started today, I hope, after listening to this. So the first thing I'm going to point you to is we have a guide on GitHub available, which is getting started on Graviton. This is continually updated with various tips and tricks, as well as applications that have been tested and the status of other things, as well as a way to get in touch with us. Provides various information around how do you debug things, how do you get the best performance out of it, or just where can I find more information. So I highly recommend you look at this. Also show this information at the end for you. So the first thing, particularly when we're thinking about a high performance computing application, is see if maybe that application's already been tested with an ARM-based processor, right? Because again, Graviton2 is ARM-based. And so ARM themselves, which is a company who developed the instruction set architecture, has done a number of testing across packages. And so this link here will show you a wide variety of applications that they've already tested. And they let you know, does it require any code changes to get it running? As well as what's the best configuration option? Or does it just run completely out of the box, which is increasingly common? The other part is, even if it's not on that list, or maybe it's your own application, it may work on ARM without any modifications. A lot of times, unless you're using specific, what we often call intrinsic instructions, which are specific ones for a specific processor, a lot of things will work out completely correctly. The other thing I want to let you know is it may not work on Graviton 2 right outside of the box. As I said, some might be using x86 specific instructions in there. If that's the case, you may have to find what's the equivalent ARM-based instruction. The other part is, even if you're not using any of these, you may find it still might show a bug or it might crash. And that's not because Graviton 2 is having an issue. It's that often it because the compiler for it, again, that's something that takes your source code and moves it into what gets executed on the hardware, provides different memory layouts or may optimize differently. So it may expose a latent bug. So basically a bug that's always been there, but you didn't see before because the compiler you used, the CPU you used, just never showed it to you. And in fact, we have a recent example. We're working with another numerical uh, forecasting code called MPass. And we saw that in some scenarios, it just didn't, it crashed, right? And working with the HPC team at ARM, they were able to look at it and determine, actually, there's a bug in here. We're not passing the right dimensions to this array in Fortran, right? And so after fixing that, it was able to work. But it wasn't an ARM bug. It was a bug that was always there, but just wasn't seen on any x86 platforms. So keep that in mind. Now, the link at the top has a number of different resources around, specifically what you can do to better develop on this platform. It's really outside of the scope of this particular webinar to go through all of those components. But a lot of times, if you're using standard applications, these can work without a lot of modifications. Last thing I want to mention is try to use a newer version of GCC to obtain better optimization. So versions 9 and above generally have optimizations for the N1 core that I was talking about before. That's part of the Graviton 2. You'll generally get better performance if you use that. Now, the next part will be, how do we really run our HPC high performance application on Graviton 2? Easiest way to do this is to use an AWS product called ParallelCluster. This is really an open source tool that allows you to generate an elastic HPC cluster that's probably very similar to ones you've used in the past. It generates a shared file system, so all of the nodes in your cluster can see the same files. A scheduler, it can provide Slurm, which is a very common job scheduler, as well as an MPI library that's ready to use and optimized for Elastic Fabric Adapter, which is our high-speed network. It also supports a wide variety of instance types. So you may already be using it today for our Intel or AMD-based platforms, but it also supports Graviton 2. So again, full instructions on setting up AWS ParallelCluster is not something I'll be able to go through in this particular webinar. However, we do have another webinar that shows a full walkthrough of setting up and running your first HPC job on AWS. I'll also have other links to ParallelCluster at the end of this presentation. What I do want to discuss in this webinar is, what specifically do you need to change for Graviton 2? And at left, you have a partial listing of a ParallelCluster configuration file. There's really only 2 changes that you need to make. The first one is change what your primary instance type is. So that's the one that you're going to log into, you'll compile code on, you'll submit jobs from. You want to have that be a Graviton2-based instance. So depending on your requirements, that may be a C6G-based instance or an R6G-based instance. Often these don't need to be particularly large because you're not running the end workload on it. So you can see I did a 2 extra large. Below, you'll see I've specified the instance type for our compute resource to be a C6GN 16 extra large. So that's a full-size instance. So it has all 64 cores, and it also has 100 gigabit networking, as well as Elastic Fabric Adapter capabilities. Those are really the only 2 changes that are needed. You just want to make sure that both your primary instance type and your compute instance type are both of the Graviton, both use Graviton, right? Because if you compile something on a primary node that was Intel and then tried to run it on a ARM-based node, it wouldn't work. So you want those to be the same. So here I'm going to show you a short demo of how do you set up ParallelCluster and what does it look like. So here, this is sped up. You can see here's a configuration file I already had that I was using for an Intel-based instance. I just went in, I'm just changing it from a C5 to a C6G. So literally everything else stayed the same. Now, if you've not used ParallelCluster before, you can see this is a pcluster command that allows us to easily create these things, these elastic clusters from a configuration file. So you can see here, I'm creating a cluster called Graviton2 example from that configuration file that I just edited. Now behind the scenes, this is creating everything possible to create that elastic cluster for you. And by elastic, I mean you can log in and there's no compute nodes there. Why pay for something if you're not using it? But if you submit a job, the scheduler will understand, you need maybe 2 nodes or 8 nodes, and it will start those up, run your job, and similarly, if there's no other activity and no jobs in the queue, it will then shut those down. All of this is configurable, so you can have variety of number of nodes. So it looks like cluster is up. We can use the pcluster SSH command. I logged in. Sinfo here is a slurm command, and you can see I have 16 nodes available, all of them there. I said, run your code, right? It's ready for you to be able to run your applications there once you've compiled it. You can see as well, I have a /shared, which has 20 gigabytes of storage there, which will be available on any of these compute nodes when they launch. There's a whole host of configuration options that you can have here. You can set it up again, like I mentioned, with Lustre, which is a parallel file system. You can set it up with larger sizes. You can configure it so you can never launch more than a certain number of nodes, right? If you say, I don't really want to ever run more than 8 at a time, you can limit it. There's a variety of configuration options that are incredibly powerful with ParallelCluster. All right, so with that in mind, we now have a cluster available. So we need to get back to our application. So what does it take to compile WRF or WRF on Graviton2? The great part here is it doesn't require any changes to the source code. Like I said, this is not an uncommon thing. There's many codes that don't require any changes in order to run on ARM-based platforms such as Graviton2. I'm not going to put all of the configuration options here, but the particular site here, again, the ARM HPC site, has some of the configuration parameters that you're going to find that will give you higher performance. Some of that's just going to come from saying, hey, make sure you optimize for this particular processor, optimize for the Graviton processor, and not for any generic ARM processor, right? Because we know we're going to run it on Graviton2, not say a Raspberry Pi, which is also an ARM processor. So by allowing it to know it's using this particular processor, it can better optimize. That's a very common thing with both Intel and AMD platforms as well. So this shouldn't be a big change from probably what you're used to already. Now it's built. So now what? This is not and I'm going to give you a couple things here to think about, but neither of these are specific to Graviton2 as much as it is anytime you're changing an instance, particularly when there's big changes in how the performance may occur, as is the case with Graviton2, you want to reassess things like OpenMP threads to MPI ranks. So many numerical weather prediction codes have the ability to assign multiple cores to a single MPI rank. So in the middle here, I have an example that shows I have 64 MPI ranks and there's 1 thread per rank. It's a very common model as well in HPC codes. Right? So anytime you want to send data or share data with another process, it is explicitly sent or shared through an MPI operation. However, for a lot of applications, they can be better optimized if they're able to share some of the data through OpenMP. Right? So OpenMP allows you to do parallelization through threads. So the example on the right is saying, let's do 8 MPI ranks on this particular chip, and each rank has 8 threads per rank. So the way you're going to configure this is specific to your MPI library, as well as if your application that you're using supports it. But again, many numerical weather prediction models do support this, including WRF. So when we see our performance results, we'll see that we tried various sort of iterations of these. However, your model will likely be different. It depends on what you're forecasting. Second part I want to touch on is I/O. So as we spoke about at the beginning, I/O happens at the beginning as well as throughout a numerical weather prediction application. So if you're possible, use a parallel file system for large workloads. You may have heard of Lustre before, and AWS provides a managed version of that called AWS FSx for Lustre. Great product. I don't have a lot of time to share you all of the details, but it has interesting features that allow you to pull in data from S3 Object Store, use it, and when you're finished, push it back. So create a file system only when you need to run it. Again, that's a feature available within AWS ParallelCluster. Next, investigate I/O options within the application. So for example, WRF has options for quilting, which means it sends data off to another node that's not doing computation, that's just doing I/O. So it takes in I/O operations that you need to write out very quickly through the network, and then does the slower write to disk, while the rest of those processes all continue computing. Also, other output options, parallel net CDF, using multiple individual files per rank or combined files. Again, depending on your use case, some of these may provide better performance than others, and it can make a material impact on your overall solution as well as cost. Next, so we've built the application. We've thought about all of the areas we might want to optimize. Now, what's the performance? So before I show you the numbers, these are the 3 different instances that we evaluated. First one is a C5N 18 extra large. It's an Intel Skylake generation processor. And you can see it has 2 sockets, and each of those sockets has 18 physical cores. So there's a total of 36 physical cores per instance. It's also optimized for HPC, so it has 100 gigabits of EFA enabled. And again, EFA is our custom hardware that allows us to bypass the operating system and increase performance when we're doing communication across instances, which is again very common in HPC. Next one we're going to do is the C6G 16 extra large. So this is a full Graviton2 processor, so it's all 64 physical cores, but it has 25 gigabit networking and not EFA. Then probably the better comparison to C5N is the C6GN 16 extra large. That has 64 physical cores again, but it does have the 100 gigabit EFA networking adapter. And in this evaluation, we are using WRF, specifically WRF version 4, and we're using the data set that I have noted at the bottom. Note that the WRF 4 data set, CONUS 2.5 kilometer, although there was also a WRF 3 version with the same name, they are different. So don't try to compare the performance across the two. All right, with that in mind, here's the first version. This is single instance performance. So we're only using one instance in order to forecast that particular benchmark solution. Now, the first thing I want to show you is the y-axis, which is the simulation speed. So the simulation speed is how much of how much time am I simulating for every time unit that I am actually having to compute. So you can think of this as if the sim speed is 1, it means It took me an hour to compute, and I can tell you what it's going to be like an hour in the future. So again, that's probably not real useful. So if you look at these numbers, they're hanging around one, right? The C5N 18 extra large gets to 1.13, which means I'm gonna chew on solving this problem for an hour, and I will give you the forecast for this problem in a little bit over an hour. Right? Not real useful, and this is a great example of why we need to parallelize across multiple instances. But showing you this is useful because it allowed us to investigate a couple different aspects. So one was one we talked about, which was MPI tasks per node. So this is, how many threads there are, how many MPI tasks. So if there's 64 MPI tasks, it means there's one thread in the ARM side here. So you can see kind of the Goldilocks zone here for the Graviton-based instances was 16 or 32 MPI tasks per node. So that's 4 or 2 threads per rank. Looking on the C5N side, again, it will vary, and you can see for this when you're running on a single node for this particular work set, it was 18 MPI tasks per node, so 2 threads each. The part you want to keep in mind here is this will change as you continue to scale and based on your particular what you're forecasting. So what I see here is great for this particular benchmark we're running, but for your workload, it may be different. And so you really want to test as you scale up, as well as when you change your model parameters as to what is the best option for you. Now, other part I want to show you here is I have 2 bars in each of these graphs. Often in HPC, we know that using a specific compiler, especially when you're using an Intel platform and an Intel compiler, can give you a performance boost. So we can see here, again, this was using GCC 10.2. It's, on this WRF model, it's considerably slower in some cases, right? We can see we're getting a sim speed of 0.93 versus 1.4, essentially. That's a material difference. And so if you want the best performance, right, the Intel compiler there on the C5N is the one you choose. Looking at the Graviton2 side, there's not a big difference here. And really that's great news for all of you. It doesn't mean that you need to think about another compiler. But if you want support, ARM is available to provide that as an offering as well. And so in the next slides, I show you, we've used the most performant one. We've used GCC for Graviton2 and the Intel compiler for the C5N results. The other thing I want to point out is on a single instance basis, you can see the C5N is a little bit faster, right? The best speed on the Graviton2 node here was, 1.079 versus 1.136. So it's a little bit faster, maybe about 5% faster than the Graviton node. Next part will be, how does this change when we scale it up? So this graph is showing these graphs are showing the same data, but in 2 different ways. The left side is showing you the performance, and again, this is simulation speed, so the same metric we talked about before. And we're showing you by instance on the left and by cores on the right. Now, you see that the green and the blue, which is the C6GN and the C5N, basically overlap each other completely on the left-hand side, which means on an instance-to-instance basis, they perform almost identically, which is really great. Although some of you may say, well, look at the right-hand side of this, right? The C5N is using for a lot less cores is able to be able to get that sim speed a lot easier. Right, but the part to keep in mind actually is if you think about a C5N, that's a 2-socket platform. In each socket has 6 memory channels versus the C6GN we talked about before. The cores aren't necessarily as performant, but we have more of them. And that particular socket only has 8 memory channels. So we're able to match the performance using 64 slightly less powerful cores with 8 memory channels compared to 36 more powerful cores with 12 memory channels. And for those of you who are familiar with numerical weather forecasting apps, the memory performance is a key element of the speed. It's also a key element in many other HPC applications. This is a very interesting result here. Now, the next part is I have this orange line. Remember, that's the Graviton line that doesn't have elastic fabric adapter. And you can see for small numbers of instances, 8, 16, even up to 32 or so, you can get pretty much the same simulation speed without having to use those instances that have that additional capability and the additional cost. However, when you really want to scale up and you want that higher simulation speed, you see that there's a huge benefit to using the elastic fabric adapter and the additional networking that's available with the C6GN. Now, performance is one thing, but we're often trading that off against cost. And this is, a little bit of a different graph than many of you have seen before. And so now simulation speed is on my x-axis. So the further to the right I am means how much faster I'm running. So again, 1 would mean I simulate an hour of time in 1 hour. On the right-hand side here, if I'm about 100, it means for 1 hour of computation, I can provide 100 hours of forecast, which is, generally quite good. And the other part on this graph here, so the y-axis is what is the cost? Obviously, lower is better. So this takes into account not only the cost of the instance, but also how long it takes to run. So if it's maybe more expensive, but it takes less time to run, it will show up in that cost there. And you can see here that both the blue and orange lines are both significantly below the green, which is our C5N platform. So what this tells us is those are a more price performance solution across the board. So even if I said I absolutely need a simulation speed of, say, 80, it looks like approximately 80 C6GN instances will give me the best price to do that. And it's about 30% more in some cases to use the C5N to get me the same results in about the same time. Now, the orange line here, remember we saw this before where for smaller instance counts, we didn't necessarily need all of the power of the C6GN. You can see if I only need a simulation speed of maybe 20, right? That's maybe enough for the use case I have in mind. I could do that cheaper using the C6G, right? And so I suggest you really look at what you need for your application because you can save money if you don't really need it. But again, if you want the best performance and be able to scale the most, the elastic fabric adapter is going to give you that. So again, what we see here is not only were we able to sort of match performance with the C6GN compared to our C5N, but we're able to do it at a dramatically lower cost of about 30%. All right. So let's go through a little bit of a review because we've covered a lot today. So first, we kind of went through the background of numerical weather forecasting, and it's really a demanding workload. It's not something that's easy. And Graviton2 is a powerful processor, and it's different from maybe what we've used before because it uses the ARM instruction set. Running on Graviton2 can easily be done using ParallelCluster to create an elastic HPC environment. Many applications may already work with ARM, but again, some might not. Some might not because they use specific x86 instructions, or they might just have a bug in it that hasn't been fixed because they haven't seen it on an x86 platform. We also talked about application considerations. So WRF, as an example, can be built very easily with just a few configuration options. But as when you're doing with any other system, calibrate your settings. So look at OpenMP, MPI thread mappings, and IO options. Next, we looked at those performance results. So on our evaluated data set, the CONUS 2.5 kilometer, WRF showed a 30% price performance improvement using C6GN over the C5N instances. Here are some of the resources I spoke about throughout the presentation. So again, Graviton2 Getting Started Guide. Start there. See what's all of our resources about Graviton. Next, if you want to get started today, go to this link here on AWS ParallelCluster. It will show you how to deploy an HPC cluster and get started. Next, I have the ARM HPC applications list. So many applications have already been ported and run by their team, and it's a great way to get started. And last, we'd love for you to get in contact with us with any sort of questions, or if you're interested in running your application on Graviton2. So feel free to check out our link there at awsamazon.com/HPC. We also have a contact us link there as well. So with that, I really invite you to try Graviton2 for your workloads today. And again, start with AWS ParallelCluster to set up your environment and try it out. Super excited that all of you joined me today, and thank you very much. And I believe now we can answer a few questions. Thanks.